Hello and welcome back. In this video, I want to discuss how we calculate the work that is done by a force that changes as the object is moved. So, in nature, there are a lot of different types of forces that depend on the position of an object. For example, the force that is exerted by a spring depends on how far the spring has either been stretched or compressed. So when we try to calculate the work that is done when compressing a spring, we can't simply say that the work is equal to force times displacement times cosine of the angle between the force and the displacement. The reason is that as the spring is displaced, that is, as the spring is being compressed or stretched, the force that is exerted by the spring is always changing. So I don't have just a single number that I can plug into this. So the way we do this is by using calculus, and it turns out that in the end there's a very simple geometric interpretation of this result that we'll be using in this class. But I'd like to explain where this result comes from. So what I'd like to do is first consider what happens when you compress a spring by a very, very tiny amount. I'm going to call this distance lowercase delta x. So when this happens, the spring does a very, very tiny amount of work that I call lowercase delta w. And this is equal to the initial force that the spring exerted before it was moved by this distance, delta x, times this very small distance, lowercase delta x. So for example, we could use this to approximate the work that is done by a spring when the spring is compressed by a very small distance, let's say like 1/1,000,000th of a centimeter. Now the question is, how do we use this to calculate the work that is done by something like a spring when the spring is compressed or stretched by a very large distance? So for example, what if I want to calculate the work that is done when you compress a spring by 1 centimeter? Well, the way we can do this is we can simply break up that motion, the compression of a spring by 1 centimeter, into a whole bunch of different parts. So I could break this up into 1,000,000 segments, where during each segment I'm compressing the spring by just 1/1,000,000th of a centimeter more each time. Then the total work that is done by compressing the spring by 1 centimeter is equal to the sum of the work done during each one of these steps. And in this case, then I can use this approximation for each one of the steps. So the work that is done during any individual step is equal to the initial force that the spring exerted before we take that step and we compress the spring by this 1/1,000,000th of a centimeter times the distance that we compress the spring, which would be, in this example, 1/1,000,000th of a centimeter. This type of sum is what is called a Riemann integral, and it's something that's used a whole lot in calculus, but it turns out it has a very simple geometric interpretation. So to understand this geometric interpretation, I want to look at a very simple example. I want to look at the work that is done when a constant force pushes an object through a distance delta x. And in this case, we know that the work that is done is equal to the force that is parallel to displacement times the displacement of the object. So if I plot a graph that shows force parallel to displacement versus the position of the object versus its displacement, what we can see is that the work is equal to the area under the force versus displacement graph. Right? This works because, remember, the area of a rectangle is equal to height versus width. And in this case, the height of the rectangle is the force parallel to displacement, and the width is just the displacement. So in fact, the area of this rectangle, which is height times width, is equal to force parallel to displacement times displacement. So the question we want to look at is the work equal to area under a force versus displacement graph, even when the force is changing? Well, remember that when the force acting on an object changes, the way we calculate the work that is done is by using a Riemann integral. And so what I have shown here is a force that changes as the object moves. And in the same graph, I'm showing a Riemann sum, where I've broken this up into 5 steps. So remember, the idea behind the Riemann sum is that I assume that during each step, the force remains constant. So at this point initially, the force that is exerted by this force is 0. So I assume it remains 0 as we push the object through this distance right here. Then After this, the force is going to be something like this, so I assume the force again remains constant during this next step. So we broke this up into 5 little segments, and I assume that during each little segment the force remains constant. Now remember that when the force remains constant, we know, at least in that case, that the work that is done by this force is equal to the area under this curve. So I know that the work that is calculated using this Riemann sum, where I've broken this thing up into 5 little sections, and I assume the force is constant during each section, that's equal to the area under these little rectangles. So we can see the area under these rectangles is kind of close to the area under this whole curve. But what happens if we go ahead and we do something more precise? Let's say we break this up into more little sections. So in this next slide, I've broken this up into 20 little segments, and we can see that the work that I calculate when doing this Riemann sum, that's the area under these little rectangles, is getting very close to the area under the force versus displacement curve. Now, if I take things a little bit further, here I'm using 100 segments. Okay, so I've broken this up into 100 little sections, and I've calculated the work that is done during each little section. And each one of these little horizontal bars represents the work that is done during each little tiny segment. And we can see that the area of these horizontal bars is indeed getting very, very close to the area that is under the force versus displacement graph. So, in fact, a Riemann integral, when you geometrically represent it like this, is going to approach the area under the force versus displacement graph. So another way we can calculate the work that is done by a force that changes as the object moves is it is approximately going to be equal to the area under a force versus displacement graph, or actually precisely equal to the area under a force versus displacement graph. So let's go ahead and look at a simple example. Here I'm showing the force that is parallel to displacement versus displacement, and I'm just asking you to calculate the work that is done. So again, the work that is done when a force varies as the object moves is just equal to the area under the force versus displacement graph. So it's just this area of this triangle. And remember, the area of a triangle is 1/2 base times height. And in this case, the height, right here, this is 62 newtons. And the base is 1.6 meters. So when I plug these numbers in, so we have 1/2 times base, which is 1.6 meters, times height, which is 62 newtons. If you plug this into a calculator, you see that it is equal to 49.6 joules. So that's the amount of work that is done by this force when it moves from this initial position here through a displacement of 1.6 meters. So now going back to the example of springs, let's see if we can calculate the work that is done when a spring is either stretched or compressed. So let me go ahead and open up a blank screen here. And the idea is that we know that the force that is exerted by a spring is given by this formula right here. It's equal to the spring constant times the distance that the spring is exerted. And remember, there's a minus sign in here which indicates that the spring force is always going to oppose the motion, right? So when you compress a spring, the spring force is pushing back on you, okay? So what this means right away we can say is that the work that is done by a spring is always going to be negative because it always opposes this displacement. Now, the way we calculate the work that is done by a force that changes as the object moves is we say it's equal to the area under a force versus displacement graph. So let me go ahead and just show, here's displacement, and here's the force that is exerted by the spring that is parallel to that displacement. And according to this formula, it's minus the spring constant times delta x. So it's going to look something like this. So if I graph force versus displacement, the force that is exerted by the spring looks something like this. And the slope of this line is equal to my spring constant. So at some point right here, let's call this delta x. At this point, the force that is exerted by this spring is going to be equal to minus k delta x, just according to this formula. So the area that is under this, what we're looking at trying to calculate is we're trying to calculate this area here. So this area, this is obviously the area under a triangle, and we know that this is going to be equal to 1/2 base times height. And the base of this triangle is going to be equal to this distance delta x, and the height of the triangle is equal to this force, which is minus k delta x. So if we plug all this in, we have the base is delta x, the height of the triangle is minus k delta x, so we see the work that is done by the spring is minus 1/2 k delta x squared. So this is the work that is done by a spring whenever the spring is compressed or stretched by a distance delta x. Now, one thing to notice about this is that the work only depends on how far the spring is stretched or compressed. So what this means is that the force that is exerted by a spring is a conservative force. So like all conservative forces, we can define a potential energy. And remember, the potential energy is equal to minus the work that is done by this force. Since the work that is done by a spring is equal to minus 1/2 k delta x squared, the potential energy that is stored in a spring is equal to 1/2 k times delta x squared, where delta x describes the distance that the spring has been stretched or compressed. So let's go ahead and look at a few examples. This first example says, a spring-powered pellet gun fires a 2.1 times 10 to the minus 2 kilogram pellet straight upwards. The spring has no mass and is compressed by 9.1 times 10 to the minus 2 meters. The pellet rises to a maximum height of 6.1 meters. What is the spring constant of the spring? So again, let's write down what we were given. So we were told that the mass of the pellet is equal to 2.1 times 10 to the minus 2 kilograms, and that the distance the spring is compressed is equal to 9.1 times 10 to the minus 2 meters. So the spring is going to fire the mass straight up into the air, and the maximum height that this thing is going to achieve is 6.1 meters. And the question was, what was the spring constant of the spring? So let me kind of draw a little picture of what we have going on here. So initially, we have something like this. We have a spring that is compressed, and on top of it is a mass. And in the final situation, the spring is no longer compressed, and the mass is going to go all the way up to a maximum height. And remember that when an object is launched vertically up into the air, at the maximum height, the object's speed will be 0 meters per second. Now, because the only forces that are present during this whole thing are conservative forces, we can say that the initial energy of the system is equal to the final energy of the system. Right, we can say this because there's only two forces that are acting on this mass. There is the spring force and the gravitational force, and both of these forces are conservative. So we know that energy will be conserved. Initially, the mass is essentially at this let me call this point right here h equals 0. So this is 0 height. So initially there is no gravitational potential energy. However, the spring is compressed. So initially there is energy stored in the spring. So there is potential energy in the spring initially. Now, once the mass reaches its maximum height, the spring is no longer compressed. So there's no energy stored in the spring. However, the mass is now at a height h above the ground. So now the mass has gravitational potential energy. So in the final scenario, there is gravitational potential energy. So plugging in the formulas for the gravitational potential energy and the spring potential energy, we have 1/2 k delta x squared, where delta x is the distance the spring has been compressed. And once the mass reaches its final height, all of the energy is turned into gravitational potential energy, and this is given by mgh. So plugging in, actually just solving for the spring constant, we see the spring constant is going to be equal to 2 mgh divided by delta x squared. And now if we plug these numbers into this formula, I know the mass, gravity is 9.8, I was given the height is 6.1 meters, and the distance the spring was stretched is 9.1 times 10 to the minus 2 meters. So if I plug all those numbers into this, I see that the spring constant is equal to 303 newtons per meter. So this is how we solve this problem. The idea, right, is just that initially there's energy stored in the spring, and in the final situation, when the mass reaches its maximum height, all of its energy has been converted into gravitational potential energy. So using this, we can solve for the spring constant. Now let's go ahead and look at a somewhat more difficult example. This example says a 2 kilogram object is vertically hung from a spring that has a spring constant of 50 newtons per meter. The object is pulled downwards by a distance of 0.2 meters, and I'm going to call that point, that bottom point, h equals 0 meters. At this point, the mass is going to be released from rest. And we know that when you do this, if you take a mass that's hung from a spring and you pull down on it and release it from rest, the object is going to oscillate up and down about its equilibrium position. And what we're asked to do is calculate the kinetic energy, the gravitational potential energy, the spring potential energy, and the total potential energy when the mass is initially at h equals 0, remember that's the bottom of its motion. When h equals 0.2 meters, that's when the object passes back through its equilibrium point. And when h equals 0.4 meters, that's when the object is going to reach the top of its trajectory. So we have a 2 kilogram mass that is hanging from a spring that has a spring constant of 50 newtons per meter. And so the idea behind this is that we know when you hang a mass from a spring, the mass stretches the spring until the force that is exerted upward by the spring cancels the force due to gravity. And I'm going to call this point x naught. So this is the equilibrium point for the mass. And we're told that the mass is pulled downwards from this point by a distance of 0.2 meters. So I'm going to call this point right here, so this is x naught. This point down here is going to be h equals 0 meters. This is the lowest point that the mass reaches. Now we know when you pull a mass away from its equilibrium point and release it, it's going to oscillate up and down about its equilibrium position. So if I plot the position versus time, so maybe I'll call this y versus t, it starts out down here at the bottom, and it's going to oscillate up and down. And the motion is going to be simple harmonic motion. So we know if we pull it down, and the lowest height is h equals 0 meters, so it's been pulled down 2 meters from its equilibrium point, eventually it's going to go all the way up to 0.2 meters above its equilibrium position. So at the maximum point up here, h is going to be equal to 0.4 meters. And so the idea is that we have these 3 points here. We have h equals 0 meters, this is the bottom of its oscillation. We have h equals 0.2 meters, and this is the equilibrium of its oscillation. And then h equals 0.4 meters, and this is when the mass reaches the top of its oscillation. And we're asked to calculate the spring potential energy, the gravitational potential energy, the kinetic energy, and total energy for each of these 3 stages. So I want to go ahead and start out with when the mass is at the bottom of its motion. Now, the thing to understand about this is that even when the mass is in its equilibrium point, the spring is already stretched. So the potential energy that's stored in the spring when the mass is at the bottom of its motion is not just 1/2 k times 0.2 meters squared. Because the distance that the spring has been stretched is not just 0.2 meters. It's the distance that the spring gets stretched when the mass is just hanging there, plus 0.2 meters. So, in other words, it's going to be x naught, the distance the spring is stretched when it's in equilibrium, plus 0.2 meters. And we'll take that and square it. So the first thing we need to do is figure out what this equilibrium position is for the spring mass system. And of course, this occurs, let me go ahead and draw a picture of this. So we have a spring here and a mass. And there are 2 forces that are exerted on this mass. There's the force due to gravity that points down, and then there's the spring force, the force due to gravity that points down, and then the spring force that points up. And in equilibrium, these two forces cancel. So using this, we can figure out what the equilibrium position is. So the force due to gravity is mg, the spring force is k delta x, and in this case, when they're equal, I call that delta x x naught. So solving for this x naught, we can see that x naught is equal to mg divided by the spring constant. And it turns out that this is equal to 0.392 meters. So this is how far the spring would be stretched if the mass was just hanging there. Now, we're told that the mass is then pulled downwards 0.2 meters, so the spring is stretched by an additional 0.2 meters. So the total energy that's stored in the spring is 1/2 k times 0.392 meters plus 0.2 meters. And we square that. So now if you plug all of this into a calculator, you see that this is equal to 8.76 joules. So this is how much energy is stored in the spring when the spring is pulled down 0.2 meters from its equilibrium point. So this answers how much energy was stored in the spring. Let's ask about the gravitational potential energy. Well, remember that the gravitational potential energy is equal to mgh. Since we're calling this point down here h equals 0, this is our zero energy reference point, this has zero gravitational potential energy when it's at the bottom of its motion. We're also supposed to look at the kinetic energy of the system. So since the mass starts at rest, right, we're going to pull the mass down by 0.2 meters and then release the mass from rest. When the mass is down at the bottom of its motion, its kinetic energy is also 0 joules. So the total energy of the system, E total, is equal to the energy that was stored in the spring plus the gravitational potential energy plus the kinetic energy. But of course this is just going to be equal to the energy that was stored in the spring, which is 8.76 joules. So this is the total energy of the system when the mass is at the bottom of its motion. Now the idea behind this is that we know that because the only two forces that are exerted on the mass is the gravitational force and the spring force, we know that energy will be conserved because both of these two forces are conservative. So we know that when the mass returns back to its equilibrium position, if we calculate the potential energy stored in the spring, the gravitational potential energy, and kinetic energy at that point, and we add all of those three things together, we should still get 8.76 joules. So that's what I want to see, is whether or not, when we add all these together, we still get 8.76 joules. So let's go ahead and look at this. So we're looking at when the height is 0.2 meters. So when this happens, the mass is back at its equilibrium position, which means the spring is stretched by 0.392 meters. So the potential energy stored in the spring is going to be equal to 1/2 m times this x naught squared. Which, if we plug numbers into this, let me see, that's going to be equal to, I have to look at my cheat sheet here, it's 3.84 joules. So that's how much energy is stored in the spring when the mass returns to its equilibrium point. The gravitational potential energy, remember that this is equal to mgh. And in this case, h is 0.2 meters. So when we plug 0.2 meters into this, we see that the gravitational potential energy is 3.92 joules. Now we have to calculate the kinetic energy. And this is a little bit tricky, but if you remember when we discussed simple harmonic motion, when the mass passes back through its equilibrium position, the mass is moving at its maximum velocity. So we know that the kinetic energy will be 1/2 m Vmax squared. So now the question is, how do we calculate the maximum velocity for a spring mass system? Well, remember that for any harmonic motion, Vmax is equal to the amplitude times omega, where omega is the angular frequency. And in particular, for a spring mass system, omega is equal to the square root of k divided by m. So plugging this into here, we see that Vmax is equal to 0.2 meters times the square root of k over m. So now if I plug Vmax into this equation here, I see that this is equal to 1/2 m times 0.2 meters squared times the square root of k over m squared. And of course, when you square a square root, they cancel. So this is going to be equal to 1/2. The masses will cancel. So we'll have 1/2 k times 0.2 meters squared. So if I plug all this into a calculator, I see that the maximum kinetic energy when the mass returns to its equilibrium point is 1 joule. So now if I take these three things and add them up, so I take the spring energy, which is 3.84 joules, the gravitational potential energy, which is 3.92 joules, and the kinetic energy, which is 1 joule. So if I take all of these things and add them together, so energy total is equal to the energy stored in the spring plus the gravitational potential energy plus the kinetic energy, I see that once again the total energy is still equal to 8.76 joules. So now moving on to the very last case, when the mass is at the top of its trajectory. So this is when h is equal to 0.4 meters. So in this case, right, this is when the mass is all the way up at the top. So the mass, the spring is going to be compressed, the spring is stretched by 0.2 meters less than x naught. Right? So when the mass is hanging in equilibrium, the mass stretches the spring by, I think it was like 0.392 meters. So if we're 0.2 meters above that, then the spring is only going to be stretched by 0.192 meters. So the potential energy that's stored in the spring, remember, is 1/2 k times delta x, where delta x is the distance the spring has been stretched. And in this case, delta x is this x naught minus 0.2 meters, where x naught, remember, is 0.392 meters. So this is 1/2 k times 0.192 meters squared. And if we plug this into a calculator, we see that the potential energy stored in the spring when the mass is at the top of its trajectory is 0.92 joules. Now the potential energy, the gravitational potential energy, is still mgh. In this case, h is 0.4 meters. So if we plug 0.4 meters into this, we see that the gravitational potential energy is going to be equal to 7.84 joules. Lastly, we have the kinetic energy. And remember that when the mass reaches the top of its trajectory, the kinetic energy, or the velocity, is going to be 0. So this means the kinetic energy will also be 0 joules. So the total energy is the potential energy stored in the spring plus the potential energy, the gravitational potential energy, plus the kinetic energy. And if I add all three of these numbers together, so 0.92, 7.84 joules, and 0 joules, I see that this still adds up to 8.76 joules. So here we calculated the total energy at the bottom of its oscillation, the middle, and top of the oscillation, and we found that the total energy of the system was the same at every single point. So it agrees with conservation of energy. And we did this without ever relying on conservation of energy. So we actually, for example, when we passed through the equilibrium point, we actually calculated that kinetic energy using what we know about simple harmonic motion. So at this point, I think I'd like to end this video, and this will end the discussion on work and its relationship to energy. And in the next video, we're going to begin a new topic discussing momentum and impulse.